All right. Hi there for everyone watching the recording. Talking about a couple of web work questions to start here. So it says determine which of these relations are symmetric. The variables x, y, x prime, and y prime are all integers. Okay. Um, so this little tilde here, this is the relation, right? So x is related to y. The little tilde is it means x is something like y. The little squiggle means something like related to, like you're something like your cousin because you're related to your cousin, right? So that's the little squiggle. They're not equal, they're just related, right? Okay, so if and only if x times y is positive. Okay, so if x times y is positive, we're trying to find out if these relations are symmetric. So what question is it asking here for part A? So sure, that's a way of looking at it, Sean. It's asking if multiplication is commutative. Can you switch the other, switch the order of those two things being multiplied and have it be the same thing? And it is. It's not even that strong of a statement, Sean, although that's a good way of looking at it. That's not exactly right. Saying that xy is equal to y times x, that would certainly imply that if one is positive, the other is too, right? So yeah, not even asking if it's equal, just positive. Yeah, exactly. So what you said is a little bit stronger, but since the stronger thing is also true, then the weaker thing must be true. So that's a true one. And it is also, yeah, the stronger thing is true in this case. Yeah, absolutely. I agree. And so it's also true here for negative, right? Okay. X is related to Y if and only if their sum is even. So what do you think about that one? Same idea, right? Addition is also commutative, so it doesn't matter which order you add things in. Cool. Okay, good. How about x plus 2y is positive? Any ideas on part D? It does not work. Okay, good. Can you give me a counterexample? What are some values of x and y where it would be true one way but false the other way? Okay, -3 and 2. So if we have -3 plus 2 times 2, that'll be positive. That'll be equal to 1. But if we do 2 plus 2 times -3, that'll be -4. So that one doesn't work. And same thing here for subtraction, right? That won't work either because you can even use that same counter example, right? You can say it's positive one way, but not the other, right? Okay, cool. So let's see what we got here. Yep, looks good. Okay, so you also wanted to talk about number 7. Okay, determine which, same thing, but which ones are transitive. Okay, so remember transitive, that's a little trickier. It's if x relates to y and y relates to z, then x has to relate to z. Okay, so if x plus y is odd and y plus z is odd, does that mean that x plus z is odd? No. Okay, and why not? Can you give me an example with x, y, and z? A counter example, I should say. 1, 2, 3. Okay, good. 1 plus 2 is odd. 2 plus 3 is odd, but 1 plus 3 is not odd. Great, good example. Okay, how about part B? Here we have pairs that are related. If and only if x times y prime equals x prime times y. That one's gets a little trickier with the notation. No ideas on that one? Maybe, why don't we circle back to that one? Let's try this one, right? If x minus y is negative, is that transitive? Yes, it is transitive. Good, right? And we could work that out, right? Because if x minus y is negative and y minus z is negative, then we can actually do some little equations and find out that x minus z must also be negative, right? Let's just even do a simple example. If I have 1, 2, and 3, right? If that's right, because x has to be less than y has to be less than z, which means x has to be less than z, which means x minus z would have to be negative. That's a great way of looking at it, David. Yeah, perfect. Okay, how about this multiplication one if this guy's positive? Is that true? Is that transitive? Well, I don't think so. Oh, wait, no, no, you're right. I'm sorry. No, it does have to be, because if you want to get a positive number out of a product, then they're either both positive or both negative. Okay. Now, if x, y is positive, that means x and y are either both positive or both negative. Okay. If y, z is positive, that means that y and z have to also have the same sign. So for xy to be positive, the sign of x has to be equal to the sign of y, right? And then the sign of y has to be equal to the sign of z. So by the transitivity of equality, the sign of x has to be equal to the sign of z. 0 is neither positive nor negative. Yes, correct. Yep. Okay, so what about part E? Here's another one of these sort of longer ones, where we have the difference of x and y equals the difference of x prime and y prime. Any ideas there? Equality is transitive, so it's true. Okay. In that case, would B also have to be true since it's an equality-based relation? Maybe we should just guess that. Maybe, right? It does use elements from different sides. That's true. So maybe we'll just leave that as our guess for now, right? Since it's an equality-based relation, and those are should probably be transitive. B is probably transitive. Okay, fine. How about part F? If x plus y is positive, what do we know about x and y? So David, I think we can use your idea of inequalities from earlier for this one, right? So what would this one look like? If x plus y is positive, what do we know about the comparing the values of the sizes of x and y? Oh, I'm sorry. Oh, nope, I'm crazy. Nope, I was thinking negative. I'm sorry. Nope, you can't say anything about the values of x and y. All we know is that, yeah, no, I'm sorry, we can't say that. If one's negative, the other's positive, then we know something about them, right? Okay, so Sean, so the absolute value is greater than the absolute value of negative. Yeah, so So maybe, let's be careful here. I'm sorry, I misread the question. So this one's a no, you say, David. Okay. So do you have a counterexample? -2, 1, and 1. Okay, so -2 plus, well, I don't think that one's going to work because -2 plus 1 would not be positive. And I don't think that one would work either. -10, 50, -40. Okay. Yeah, I think, Lucas, I think that's a good one, right? So you have -10 and 50, that makes 40. 50 and -40, that makes 10. But -10 and -40, that makes -50. Yeah, so I think this one does not work. Yeah, that's a good counterexample there, Lucas. Okay, so let's see if we're right. Oh, we missed one. B, C, D, E, incorrect. So maybe it was this B one that was wrong. Let's see. There we go. Turns out B didn't work. And I'll leave that to you guys to figure out, right, why this one was false, even though it was inequality and equality-based relation. Okay, cool. Any other web work questions for me? Oh, and before you do that, I should say, oh, and there's a question. When you get them wrong, it doesn't say how far off you were. Yeah, that's true. Yeah, you have to be, you have to actually try pretty hard to get all the right answers in order to get 100% on these guys. I mean, it'll be pretty easy to get half credit, but to get full credit, you're gonna have to sit for a minute and figure them all out, right? Yeah, okay. Yeah, you know, they are getting harder, you know, I'll tell you that, that's for sure. So that being said, I was not able to figure out the issue with the 8.1 problems yet. If I don't figure that out by tonight, then I'll shoot you out an email tomorrow, and I'll just cancel those problems, and they won't, you know, count against your grade. But I'm going to give myself the rest of tonight to try to figure it out, and then after that, I'll just let it go. Does that sound good to everybody? Does anyone need to finish the web work today, or else there's no way they could possibly finish it? Sounds good. Okay, cool. Alrighty. Any other questions for me? Questions on proofs, labs, any other stuff like that? Collab proofs? Okay, for this week, last week, which ones?
Actually, it's probably easier for me to ask. Are you still doing the one where you mark the ones that were the best, and then you're gonna
Oh,
so
yeah.
that we can all look at them?
Yeah, I forgot to do that. Yeah, I was going to, but and I probably forgot. So okay, so let's go through and look. And we can do that for a moment. So here, all right, let's look in here. Collaborative proof 1. So let's see here. So let's see. So David had a good idea in the chat today. Let's see what his looks like. Do you mind if I look at yours there, David? No? Okay, cool. You're first on the list, so I'm going to pick on you. All right. Oh boy. So if A triangle B equals B triangle C, then A equals B. Okay, and I like that Venn diagram down here. That's a good one. So here, let me zoom a little bit. That's too much. There we go. Grab it, I grab it. Okay. Okay, so if you suppose A is not equal to B, then the symmetric difference is the union of the two areas without the area in which they intersect, right? Okay, so you've got a proof by Venn diagram. You've got a algebraic proof here as well. So yeah, so this is looking pretty good. Let's see the next page here. Okay, so it looks like you've concluded that A does equal B in that particular case. And and so here you're doing proof by elements as well. So you did it 3 different ways. Wow. Okay. So yeah, so check out David's. David's has some interesting ideas there. And then the other collab proof. And David, you think Lucas's is more complete? Okay, so we can look at Lucas's as well. And there's heterological, and that, yeah, just glancing over this, that looks correct. Okay, so let's check out Lucas's. Maybe Lucas's is more concise, right? All right, here, there we go. Well, don't worry, I've forgotten too. so let's see. Okay, so you've got, okay, so you do a little bit of algebra here to sort of figure out what the symmetric difference is saying. And you can break it up, then you're doing an element style proof. And trot through that element style proof saying, if A is not in C, then it's in B. If A is in C, then it's in B. So it goes in either way. So A is a subset of B. Okay. And there's the flip side for the second part. And then problem 2 is heterological. Yeah. So I think looking at either of those would be fine. Yeah, and I'll try to remember to highlight those in the future. So sorry, I forgot about that. Okay. As you go through, also, I think, I can highlight them and I'll try to remember to do that. But what you should be doing is you should read, at least, 3 or 4 people's proofs and see if you can figure out which ones are right and wrong. So, based on, your understanding of the material, I think you should be in a position, and by you, I mean any of you, not just Brian who asked the question. I think whoever it was, I think it was Brian, whoever it was that asked the question. All of you should be able to sort of read someone else's proof and think through the logic and say, hey, well, does this make sense or does this not make sense, right? And that was part of my intent with these collaborative proofs, is that you'll be reading other people's proofs without knowing if they're good or not, and be able to judge them and be able to figure out, oh, well, does this make sense? Is this something I believe and or not? And to extract the sort of the essence of the ideas from people's proofs and be able to, decide whether or not that's a good idea and a good way of solving the question, right? So that's sort of my intent there, is that you would read a few of those and see what you think. Right, correct and incorrect, both, right? Because they're both important. I think looking at, a wrong answer is just as important as looking at a right answer for understanding, what these proofs are supposed to be like. So, okay, cool. Okay, so does anyone else have any hint for this week's graded proof? Okay, so let me go to that. So assignments, proof 3. All right. Okay. So if R and S are relations on a set A that are transitive, is their union transitive? Okay, so what is this asking exactly? Someone just sort of speak generally about what this is trying to say. Also, if someone wants to hop on the mic, that would probably be more efficient, because if you're going to say anything substantive, it'll probably be a paragraph's worth of information. Hey,
I'm not sure if this is the right wording or idea, but so if it's just basically saying the two separate relations R and S, and if you combine them, they would still be transitive, right? So,
Uh-huh.
like all the practice we did with having the elements and the arrows drawn between them,
Yep.
if we just combine those into one relation, but I'm kind of confused how the two elements would then relate to each other.
Okay, so let me give you an example here. It's not saying that, David, it's not saying that the composition is transitive. It's saying that the union is transitive, right? So this is supposed to be R union S, right? So you take the union, each relation is really just a set, right? It's a set of pairs. And so, excuse me, and so if you take the union of these two sets, is that also going to be transitive? So let me draw you a little picture. Stop that here. Okay, so, and let me spotlight and pin. All right, great. So let's say I have some set A that has some points in it. Okay, so those are my elements of A, and I have my relation R is pink, and my relation S is yellow, right? And so I've got, let's just, for the sake of argument, we'll say that both of these relations are symmetric, just so that I don't have to draw arrowheads with this giant highlighter, because I can't really do that. So forget about which direction. We'll just say all these arrows are bidirectional, right? So let's say that's my relation R. Those 3 points are all related to each other, right? And then here's my relation S. These 3 points are all related to each other for my relation S. Now, if you take all the lines, the pink and yellow, is that still a transitive relation, right? Oh, but I needed to make sure that R and S were transitive, which I may not have done. Uh-oh. Okay, I screwed up. Wait, let me try one more time. So let's say that, let's do one more. Let's make it a little bigger. I'll just do 4 points. Okay. So if a relation is transitive, that means that if A implies B and B implies C, then A implies C. There we go. So that's transitive, right? Makes a little triangle. And then maybe we have this situation for my relation S. These guys are related, these are related, and these are related, right? So let's say that that's a depiction of my relation here, right? Now, if I union those things, is the result going to be transitive, right? Which is to say, if I include all the lines of all the colors, is that relation then going to be transitive, right? So I'll let you guys think about that. Does that help? Does that help answer your question, Haruka, of what we're doing here? It does. Okay, great. Cool. And I realize this is very abstract. I didn't even bother to put numbers. I didn't even label these elements of my set, right? I sort of sped through the idea of what transitivity is, which is that if this one relates to this one and this one relates to this one, then this one has to relate back to that one, right? And now I have made a relation R and a relation S that are both transitive. And then if I union those, is the result all transitive? So hopefully that helps a little bit. No, not necessarily. No, you can do a picture. You can do it algebraically with a algebraic derivation. It's totally up to you. Whatever you're comfy with. I mean, I think for me personally, I'm just a very visual person, and so if it was me doing it, I would definitely go for a picture. But for me grading it, I don't care. It makes no difference to your grade. But I will say that if it was me doing it, I would definitely do a picture. But that's just me. Like Cat's Cradle. Yeah, exactly. A lot of good math in Cat's Cradle. It's a whole branch of mathematics, a whole branch of topology about knot theory. That's some interesting stuff. Lots of different knots you can make, it turns out. Anyway, let's not talk about that. Get it? Let's move into 8.3. Right? And all right, where am I here? All right, there we go. All about equivalence relations. Okay. So if you'll recall, we've talked about partitions before. Does anyone remember what a partition is? Breaking a set into pieces which are disjoint, but whose union is the whole set. Good. Is a collection of subsets, a collection of disjoint subsets. What does disjoint mean? They don't contain any of the same stuff. Very good. Okay, so I think, again, a picture is nice here. So if I want to talk about some set A, right, and we have all kinds of points inside of A, here's my set full of stuff, right? And I want to partition this. Well, essentially what it's saying is, well, I'm going to take one part. It's going to look like this, right? Here's another part, right? Here's a third and a fourth part, right? So here's parts A1, A2, A3, and A4. Each part is disjoint from all the other parts, mutually disjoint. I guess I should have said mutually. Mutually disjoint subsets, which means if you pick any two subsets, they don't overlap at all. There's nothing in common, right? So this point can only be in one of the subsets, and it happens to be in subset A1, right? This point happens to be in subset A3. And their union makes up the original set. So it's not like there's one other point that's just like left out up here without being in one of the parts, right? Oh, and these guys, A1, A2, A3, and A4, these are all called parts of the partition, right? That's why it's called a partition. You're taking a collection of items and breaking it up into parts, like smaller subgroups, we could say, right? Okay. Now let's talk about the relation induced by a partition. Partition of a set has each set element related to another if and only if they live in they are in the same part. Okay, so if I take these 2 points right here, this one in A4 and this one in A2, if we're talking about the relation induced by this partition, would these 2 points be related? No. What if I took these 2 points? Would these 2 points be related? Yes, because they're both in A1. If I took these 2 points, they would not be related because that one's in A4, this one's in A2, and so on, right? So that's the relation induced by a partition. Induced means sort of created, right? Like if if a woman has induced labor, that means they made the labor happen, right? It's created, artificially by a doctor, by some medicine, right? And here it's that same idea of creation. We're creating a relation by making this partition. Yeah. Any questions there? Okay, cool. So moving right along. Okay. A relation induced by a partition is reflexive, symmetric, and transitive. And I think we can just sort of walk through this. I mean, your book goes through this whole algebraic proof, which I don't really think is necessary. I think it's pretty obvious, right? If we have a relation induced by a partition, why would that be reflexive? Can you tell me in a single sentence why that would be? Each element is in the same part as itself. Beautiful. That's exactly right. Okay. Yep. And Seth, yep, same thing. Yep, perfect. Okay, how about symmetric? Why would the relation induced by partition be symmetric? Okay, if a first element is in the same part as the second one, then the second one's in the same part as the first one, right? Okay, if here's my first one, and here's my second one, and they're in the same part, then they're in the same part, end of story. That means that the second one is also in the same part as the first one. Right? If two elements are not in the same part, right, then if we do, if this is the first one and this is the second one and they're not in the same part, well, then you can look at this one versus this one, change the order. They're still not in the same part, right? Okay, how about transitive? Pretty much the same story, just add a third element, okay? So if, let's call this, let's label these. Let's call these A, B, and C, right? So if A is in the same part as B and B is in the same part as C, well, of course, then A must be in the same part as C, right? What do you guys think? Does that look okay? Happy with that? All right. Okay, another definition here for you. Forget about partitions for a minute, just any relation that is reflexive, symmetric, and transitive is called an equivalence relation. Okay, so there's just a special vocab term, equivalence relation, which means that that particular relation hits all three, right? It satisfies all three of these, types of relations. People good on that? Maybe we should do an example. Yeah, let's do an example. Okay, so we've got some set X equals 1, 2, 3. And I'm going to think about, you have a question there. Why is it called that? What does it have to do with equality? Well, there is some intuition. So it's not equality, it's equivalent, which is not exactly the same thing, right? So equality means perfectly the same. Equivalent means functionally the same, right? Or basically the same, or mostly the same. Like if you switched them out, you wouldn't be mad, right? That's equivalent. Like if you had, it's a good example, right? If I had a Toyota Camry and I switched it out with a Honda Civic, right? You know, those are obviously not the same car, but I would say they're equivalent, right? They're both, a compact, compact sedan, whatever, they're from different companies, but it's basically the same kind of car, right? They're certainly not exactly the same car, but they're basically like equivalent to each other. It's sort of like a loose equality, right? Yes, right. So, well, David, I don't know if I would go that far. I would say those are logically equivalent, which is different than what we mean by equivalent. Well, I don't know. Now it's too complicated. So, okay, so yeah, the logically equivalent means literally exactly the same. So this kind of equivalence is not that strict, I would say. I think logical equivalence really just means equality. So I'm sorry for the terrible usage of vocabulary there. That makes no sense, right? My apologies, right? So logically equivalent really just means equal, but this kind of equivalent doesn't mean equal. And we can actually see this in the example in just a second here. So why don't I come back to that, right? Okay, so what I'm going to do is I'm going to think about a relation on the power set of X. Oops, sorry. Parentheses around the power set. There we go. From the power set of X to the power set of X. Okay. And my relation will say A relates to, or sorry, capital A, because we're doing sets here. A relates to B if and only if the least element of A equals the least element of B. So the minimum of A equals the minimum of B. That doesn't mean that A equals B. It's saying that the minimum of A equals the minimum of B. That's like saying, it's like saying it's like one particular property of A is equal to one particular property of B. Maybe I would say that the Camry and the Civic are equivalent because they get exactly the same gas mileage, which I don't know if that's true, but for the sake of argument, right? Let's say that those two cars get exactly the same gas mileage. I would say, for my purposes, trying to buy a fleet of cars for my company, okay, it's equivalent to buy the Camrys as it is to buy the Civics because they're the same price and the same gas mileage. They're not the same car, but they are the same price and the same gas mileage, right? So it's not perfect equality, it's functional equality, right? It's equality in the properties that I happen to care about right now. Does that help? Still, yeah, it does. Okay, cool. So let's show, I want to show that R is an equivalence relation. Okay, so I want to show R is an equivalence relation. Okay, so, okay, fine. So if I want to show R is an equivalence relation, I want to show that it's reflexive, symmetric, and transitive. Question, does it always apply to dealing with a specific aspect of a larger set? Always. I would say most of the time. I don't know. Can I think of a counter example? I'll say yes, David. I'll say yes. I think that's a good way of looking at it. I'm not sure if that's perfectly true, but that's definitely like almost true at least. Yeah. I'll in the back of my mind, I'll try to think of a counter example and see if I can come up with one. Okay, so we want to show R as an equivalence relation. So we want to say it's reflexive, symmetric, and transitive. Okay, so let's, yeah, always is a dangerous word. Yeah, exactly. Yeah, that was my worry. Okay, so why would this relation be reflexive? Can someone explain why that would be? Okay, so, okay, A relates to A because the minimum of a set equals itself, right? If you're taking the minimum of A and then wondering about the minimum of A, are those equal? Yeah, well, sure, of course they are, right? The minimum of a set equals the minimum of that same set. Okay, how about symmetric? Why would that be? Because of equality. Okay, that's a good way of putting it. Oops, A. Sorry, my writing got sloppy. Okay, that's reflexive. Symmetric. It is an equality-based relation, which is why it is an equivalence relation. But let's be a bit more specific, right? So for symmetric, we'll say if the minimum of A equals the minimum of B, what does that imply? Good, then min B equals min A. Very good. They're the same number. Yep, exactly. Agreed. Okay, and then how about transitive? All right, you got the whole thing. If you ever want to hop on the mic, feel free, right? If min A equals min B and min B equals min C, then min A equals min C because, again, they're just the same number. That's exactly right, Sean. Perfect. Cool. So that is an equivalence relation because it's an equality-based relation. Awesome. Okay, quick little example. Let's move it along. So what is an equivalence class? We're going to, now that we've done equivalence relation, now we're going to jump back to this partition idea. Okay, and that's where we're going to stick around for a while here. So A is a set. Let A be a set and R an equivalence relation on A, where R goes from A to A. right? For some element of A, the equivalence class of little a, which is denoted with square brackets, is the set of elements of A, big A, related to little a. Is the set of elements in A related to little a. In other words, the equivalence class of A equals the set of X in A such that X relates to little a. Okay, so to summarize, the equivalence class of something in the set is all the stuff that relates to it. This could be any equivalence relation. Yep. So it's all the stuff that's equivalent, right? Because remember, we're working with an equivalence relation here, right? So all the stuff that's equivalent, right, means it's equivalent to itself. It's if it's equivalent to other stuff, it goes back the other direction, and it forms these kind of chains of equivalence, right? If it's equivalent, A is to B and B is to C, then we know A is to C. So we have all these things that are equivalent, and we'll call that an equivalence class. That's all the stuff that's functionally the same as A, little a, right here, right? Maybe you can see where we're going with this. If I have a relation induced by a partition, what are the equivalence classes going to be? So here's the parts. Yeah, exactly, right? So if I have a relation induced by a partition, let's call this A5, so I'm being consistent here. A5, it just has one thing in there, right? So, A is equivalent to B, A relates to B, B relates to C, so A relates to C, C relates to itself, C to B, B to C, all the rules are satisfied, right? So all of these guys are equivalent to each other inside of A1, which means the equivalence class is all the things that are equivalent to each other, and that just is A1. And so where we're going with this is we're going to prove that the relation induced by a partition forms subsets that are in fact equal to the equivalence classes of A. They actually are the same thing. We're going to prove that. That's our goal, right? Is that people good with that? Any questions there? Does that sort of idea make sense? I think it's not that complicated of an idea if you're following all the little steps, but happy to go through the little steps if you need me to. Okay. Should we do an example? I don't know. Yeah, we should probably do an example. Let's do an example of finding some equivalence classes. Scooch this thing. Not quite trying to fit 7 different things on a small desk. So sorry about that. All right, so let's do this example here. Okay. All right, so I have a set A with a directed graph, and here's how it's going to look. This is just right out of your book. So I've got A. Here's what it looks like. I have 0 and 4 like this. We've got 1 and 3 like this. And then I've got 2 over here. There's my set A. With the relation depicted as a directed graph. We'll do a little circle, stay consistent here. Okay. So first of all, can someone list, you can do it in the chat or you jump on the mic, that might be faster. Can someone list, or why don't I ask you this? How many pairs are in this relation? You don't even have to list them all. Just how many are there total? Anyone see how many pairs are in the relation? More than 3. That would be the number of equivalence classes. More than 4.
So you've got 0 and 4, 4 and 0, 1 and 3, 3 and 1, and then I guess 2 and 2, plus 1 and 1, 0 and 0, 4 and 4, and 3 and 3.
And how many is that?
What did I just say? Like 7 or 8?
You listed them all. It was 9. Yeah, very good, David. Yep, 9. Perfect. All right, cool. So how many arrows are there is what I was asking, right? Because each arrow, and the double-ended ones count as 2, right? Each arrow indicates the relationship of 2 items, right? So the relation, if we're going to list out all of the pairs in the relation, that's the list of who's related to who. And that's the same as how many arrows are there in our diagram, right? Okay, so we've got 9 pairs in our relation. And the question is, what are the equivalence classes of the relation on A? All right, so first of all, how many are there? 3. Good. And what we can do is we can list out the equivalence classes this way. The equivalence class of 0, 1, 2, 3, and 4. Okay, so what's the equivalence class of 0? Zero and 4, right? It's the list of all the elements of A that are equivalent to 0, right? In other words, the ones that are related to 0, right? And the only things that are related to 0 are 0 itself and 4. Which also happens to equal what? Which other equivalence class? Yeah, the equivalence class of 4. Those are the same thing. Why? Because, well, maybe if we thought about this as a partition, right? 0 and 4 would be in the same part. See where we're going, right? How about 1? What would be the equivalence class of 1? I'm just going to get rid of these. 1 and 3, which is the same as the equivalence class of 3. And 2 just has itself. Right? Any questions there? Does that look good? Okay. So maybe we should do one more example. Okay, so we did an example where we showed that, get this guy here. We showed that we had an equivalence relation a moment ago. If we take the power set of X and equate the minimum elements of two subsets, that was an equivalence relation. We showed that a few minutes ago, right? So let's take that same setup and find the equivalence classes, right? So now what I've got is I've got my power set of X. Let me do this one over here. At the power set of X, remember X is the set 1, 2, 3. So what would be in my power set of X? In fact, maybe I'll just do it as a circle. It'll be easier to see this way. If X is the set 1, 2, 3. So what's the power set of X?
It's a set that has just 1, a set that has just 2, a set that has just 3, a set that has 1, 2, a set that has 1, 3, a set that has 2, 3, a set that has 1, 2, 3, and then the null set. I think I got all of them, right?
I think you did. Okay, 1, 2, and 3, and null set. Then you want 1, 3, 2, 3. So you want 1, 3.
1, 3, 2, 3, and 1, 2 should be in there.
And 1, 2.
And then also the set 1, 2, 3.
1, 2, 3. Okay, cool. So awesome. So that's the power set of X. I've just sort of listed them all out inside this circle here. And the question is, what are the equivalence classes, right? So first of all, how many equivalence classes are there going to be if our relation is that each subset has the same minimum element? More than 3, but you're close. So Sean, why don't you list out the 3 that you thought? Or even just
So I was thinking there'd be a subset for all of the ones that have 1 in them, because then that's the lowest element. Or a subset for all of the ones that have 2 in them, because that's the lowest element, and then a subset that has all the ones that have 3 in them. And of course, I forgot that the null set needs to
is its own. Very good. Everyone has, well, it's not that everyone has the null set. I think the null set is in its own separate part, actually, because it doesn't have a minimum element. So it's not equivalent to any of these other guys. Does that make sense, David? I see, but it's not included. Yep. Okay, I got you. Cool. Okay, so here's a partition style description of what's going on. Let's do an equivalence class style description, right? In that case, what's the equivalence class of the empty set? Just 0. Just the empty set.
Yeah, sorry, I don't have the
empty set character.
Button.
I got you. Yep, totally. Okay, how about the equivalence class of 3? This one's a little tricky. Got to get the notation right. Very good. The set of 3. Awesome. Okay. How about the equivalence class of 2? All right, awesome, Natasha. Great job. Singleton 2 and the set 2, 3. And of course, the equivalence class of 1 is this guy. I won't bother writing it out. You get the idea, right? All right, cool. So now let's actually jump into the proof that that the partition induced by an equivalence relation is actually the same as the equivalence classes, right? So we're going to start off with a lemma. Okay, and here's our lemma. Let A be a set with an equivalence relation R. A and B are elements of A. And A relates to B implies what? What can we say about the equivalence classes if A and B are both elements of A and A relates to B? What do you think we can say about the equivalence classes of A and B? They're the same. Yeah, they're equal. Very good. Equivalence class of A equals the equivalence class of B. And I'll put some parentheses on here so you see where those are supposed to go. All right. So we want to show that these equivalence classes are equal. What are equivalence classes? Like what sort of mathematical object are they? They're sets. Good. So if we want to show that two sets are equal to each other, how do we do that?
Pick an arbitrary element of one and then prove that it is an element of the other.
Good. And you have to do that both directions because you have to show that an element of here is in here to show that this is a subset of that one, and then show that this one is a subset of that one, right? You're supposed to go both ways. I'll just do it in one direction. The other direction works pretty much exactly the same way, right? Okay, so I want to show that the equivalence class of A is contained in the equivalence class of B. Oops. Equivalence class of B. The other way is the same. The other direction proof is the same. Okay, now to do that, as you said, we're going to let X be an element of the equivalence class of A. I'm going to do an element style proof, right? What do I know if X is an element of the equivalence class of A? Then X is related to A. For what reason? What's the justification for that? The definition of equivalence class, perfect. Right? If X relates to A, then what do we know? X relates to B. Good. Why do we know that? Transitivity, good. And which other, and A relates to B, good. Since A relates to B and transitivity. Now let's go through that for a minute. Okay, we have X relates to A. We found that. One of our premises is A relates to B. So you have X relates to A relates to B. By transitivity, X goes down the chain, so X relates to B. And that's what we got there. Great. Then what? We're almost done. We're trying to show that if X is an element of the equivalence class of A, then X must be an element of the equivalence class of B in order to show a subset by elements proof, right? So what's our last step? Good. X is an element of the equivalence class of B by definition of equivalence class. That's it. Going the other direction is the same, except that here we have A relates to B, and what we'd be starting with is, instead of X as an element of A, we'd be starting with X as an element of B to go the other direction. So the proof would be exactly the same, except on this piece right here, what other property of equivalence class would we need to use? Symmetry. Good. Because if we start with B and we're going toward A, then we would need B relates to A in order to use transitivity. But we do have that because we can use symmetry on this premise because R is an equivalence relation, right? So that's the only little gotcha in going the other direction, is you have to use symmetry as well. See why it's important that an equivalence relation is transitive and symmetric is because we need it in the proof right here to show that a partition is the same thing as a set of equivalence classes, right? The definitions all sort of work together, right, to make these proofs happen, right? This idea of reflexivity and symmetry and transitivity didn't just fall out of the air. They're useful ideas that were built into the definitions so that the proofs work. They're not just for fun, right? It's because they're useful, right? All right. Let's do another one. Actually, let me refill my water real quick. I'll be right back, and then we'll do another one. One moment. Okay, sorry about that. I don't have the vid. Got the vaccine and everything, just allergies. Thank goodness. All right, so let's move on. For our next one, we'll have the same setup. Let A be a set with an equivalence relation called R. All right. A and B are again going to be elements of A. Implies that the equivalence class of A intersected with the equivalence class of B equals the empty set, or the equivalence class of A equals the equivalence class of B. I didn't say proof last time. I probably should have said that, but you get the idea. All right. So this is going to be, we're going to start off with a sneaky trick. Okay. So here's the trick. If we have something of the form P implies Q or R, we can massage that logical statement into a different form that's going to be a little bit nicer for us to prove, right? What can we do to this form to sort of change it? Like what sort of logical operations could I do? Okay, good. So I can say not P or Q or R. Right? Good. So we're off to a good start. We can also use the associative property to say not P or Q or R. What could I do next? Excellent. We can transform this one into an arrow. So we'll say not P or Q implies R. And then, of course, I can distribute the not. So I'll have P and not Q implies R. And that's what I want to prove. It's the same thing. These are all logically equivalent, right? They are exactly the same thing, right? So what I'm actually going to prove is that A and B are elements of A, and the equivalence class of A intersected with the equivalence class of B is non-empty, implies the equivalence class of A equals the equivalence class of B by my trick. I'll just do by my trick. What do you guys think? Is everybody happy with that? Just switch the logical operators around a bit. Any questions? Cool. See why we did logic, right? Because if we tried to prove this, it totally wouldn't work, right? We wouldn't be able to do a nice straightforward deduction, derivation to see why this works. But if we must use logic to massage it into this other format, then the derivation is going to just fall right out and it'll be straightforward, right? Useful. Again, it didn't just fall out of the sky. It's useful, right? All right. So here's what I want to prove. Great. So what do I do? So I say, I've got these things in A and their equivalence classes intersection is non-empty. How do I then show that the A and B are actually the same equivalence class? Okay, so I'm wondering, what do I do next was the question. So I've got A and B are elements of A. I've got that the intersection of their equivalence classes is non-empty. And I want to show that the equivalent classes in that case must actually be the same. What do I know if the equivalence, not a contradiction, not quite. It's going to be a straightforward proof. If I know that the equivalence class intersection is non-empty, what must there be? There must be a common element. Yeah, exactly, right? Let's call that thing X. There exists an X in A such that X is an element of the equivalence class of A and X is an element of the equivalence class of B, right? Which is to say, there's an element that the equivalence classes of A and B share. Yeah? Is everyone happy with this step? Any questions? Okay. No questions there, I guess. Okay, so now what do we do? Again, it's a straightforward proof. So what's the next, sort of obvious step in a straightforward proof? I'm saying straightforward, that's the wrong word. Direct proof is the right terminology. Sorry about that. Direct proof. Okay, so in a direct proof, you usually want to work from the definitions, right? So what definition do you think we would want to use here? Okay, let me help. It seems like you guys are lost. So I can use the definition of equivalence class, okay? So I can say, if X is in the equivalence class of A, then of course X relates to A. If it's in the equivalence class of B, well, then it must also relate to B by definition of equivalence class. See where I can go from here? We don't want to use the lemma from before. it's the same style, but so we're going to use a similar idea, but we're not going to actually use that lemma. Lucas, we do want to show that A relates to B by transitivity, because if A relates to B, then their equivalence classes are the same. So Lucas, you're going the right way, but the way we have it set up now, we need symmetry first. That's exactly right, David. So what we can say is A relates to X and X relates to B by symmetry, because I just switched this one around, right? Right? Then we have A relates to B by transitivity. And finally, we have now we can use that lemma, right? That if A relates to B, if A relates to B and A and B are both in A, which is what we have A and B are both in A, and A relates to B, now we use the equivalence class of A equals the equivalence class of B by previous proof. What do you guys think? Good? Questions? Makes sense. Okay. So now here's what we've got. We've got an equivalence relation called R, which forms equivalence classes who have a empty intersection, right, between any of the equivalence classes, or they're just equal to each other, right? So we know that the equivalence classes at this point are going to have are going to be mutually disjoint, right? So by this proof, we know that equivalence classes will be mutually disjoint. Right? Now we're halfway to the definition of partition, right? Because a partition has subsets that are mutually disjoint. What else do those subsets have to be to make a partition? Yeah, their union is A. So the only thing that remains is to show that, so what we need to show, what remains is that the union for all A in A of the equivalence classes of A, little a, equals big A. Let's see if you all follow this notation, okay? This is a big union, like a summation, right? This is a big union of lots of stuff. What am I unioning? Well, I'm unioning over all the elements of little a inside of big A. And if I take the equivalence classes of those and union them all together, I'm going to come out with my original set big A. Right? So David, that's what you said. You had the two important parts. You had the union and the A, and I just filled in a couple of the little details. Right? Any questions on that? Okay. So what do you guys think? How's this last part going to work? Okay, and let me ask you some leading questions. What are these objects? What is this union of equivalence classes? What is this A? What are those things mathematically? Sets. And if we want to show that two sets are equal to each other, what do we got to do? Subsets both ways. Very good. Okay, so what we want to show is two parts. We want to show that the union of all the equivalence classes of the elements of A is a subset of big A. That's one side. The other side is A is contained in the union of all the equivalence classes. Yeah. Okay. So now we want to do a subset proof. So what style are we going to do? Proof by elements. Very good. So I want to start off, let X be an element of what in order to prove this guy? Okay, the union of the equivalence classes. Very good. And over on this side, we'll have let X be an element of what on the other side here? Big A. Perfect. Okay. And then we're going to show on the left that X must be an element of big A. On the right, we'll show X must be an element of the union of equivalence classes, right? Okay, so now I'll finish out one side before I go to the other. I'll stop going back and forth. I think that's confusing. So let me stop doing that. Okay, so let's stick on the left for a minute. Okay, so we've got X is in the union of equivalence classes. What do I do next? Okay, X relates to little a for each A. Not exactly. It doesn't relate to each of them. How many little a's does X relate to? At least one, right? We only need one of them, okay? So we know from here that if X is an element of this union, okay, then it must be an element of at least one item in the union. Yeah? So let's, maybe we should label these, right? So we'll say X is an element of this union, which is, you know, let's do it like this. We'll call it little a1 union equivalence class little a2 union ... Right? We'll give these, we'll number these things, and I think that'll make it easier, right? If X is an element of this union, then we know that there is some a equivalence class of a sub I where X is an element of the equivalence class a sub I. So let's talk about that for a minute, because that's not simple, okay? If you have a union of a bunch of stuff and something is inside that union, then you know that that thing must be inside at least one of the sets being unioned together. Do you believe me about that? Can you visualize that? Like if you have, you know, if you have a bunch of things being unioned together, and you have some point X that's in that union, right? Let's say that this is all, we're unioning these three sets together, and X is somewhere in that union. Then you know that X has to be an element of at least, maybe more than one, but at least one of those items. Maybe if X lived up here, then it would just be an element of, only A, instead of, this X would be an element of both B and C that are union together. But do you believe me that this X has to be an element of at least one of those guys? If it's out here, right, this is X, right? Then it couldn't be part of the, if it wasn't part of the union, right, then it won't be inside of at least one of A, B, or C, right? David, you have a question. Since it's an equivalence relation, doesn't it have to be only one? Yes, but we don't. I guess we know that at this point, but yeah, and that's true. But I guess we don't need that, is what I should say. So yes, that's totally true. But all we need is for it to be inside one of them. Yeah. Yep. Okay. So now what do we know? So X is in one, not some. X is in one of these equivalence classes. Okay, fine. Now what do we know? X relates to A sub I. That's true, but that's not the direction we want to go. X is in A. Okay, Y? You're right, but there's one step missing. Which definition of equivalence relation? Good. All of the equivalence classes are in A, right? Since all equivalence classes are subsets of A, X must be in A. You got it. Good. Okay, let's try the other side. Okay, now we've got X is an element of big A. Now what do we do? Now here's where it gets a little, well, these are both sneaky. These are both pretty sneaky. Yeah, that's what we want to show, David. That's right. We want to show that X is in some equivalence class, A sub I, right? Now, how do we get there? Not expanding the union. Nope. It's sneakier than that. It's very sneaky. The definition of a relation induced by partition. Not quite. No. Any other ideas? All right. So we know that for anything inside of A, that the relation is going to work on it, right? So we know that X is going to be related to something. What is X related to? There we go. Very nice. It relates to itself by reflexivity. Right? Sneaky. Where can we go from there? Then we say it must be in that equivalence relation. Good. Since X relates to X, we know that X must be an element of the equivalence class of X by definition of equivalence class. Right? Now what do we know? Good. Then X must be in the union of all of them, right? In the union of all equivalence classes. Since this is, the union of all of them. So if it's in one of them, then it must be in the union of all of them. Since if X is in one equivalence class, it must be in the union of all of them. What do you guys think? Is that tricky enough for you? So in the last three proofs, we've used all of reflexivity, symmetry, and transitivity, some of them multiple times, right? The definition of equivalence class, right? This big union. This is kind of the coup de grace of the first 3 weeks here, right? Is proving that the equivalence classes over a set form a partition, and vice versa. A partition also forms the equivalence classes. They're equal, right? Questions, comments? What do you guys think?
So is the idea that eventually we'll use this idea of equivalence relations to talk about like a special set of relations? Like, what is the point of equivalence relations, I guess?
Great question. That's exactly where we're going next. So we're going to begin talking about actual examples of equivalence classes and the notion of an equivalence class forming a partition and the equivalence of those two ideas. I won't say equivalence. The fact that those two ideas are the same of equivalence classes and a partition is going to be really helpful as we try to work through examples of specific equivalence classes and specific partitions. Does that make sense? Maybe it will make more sense when we do some examples. Right? Okay, yeah, that was a good question. Other questions? Okay, So I did want to say that this proof is in your, all the proofs we did today are in your book. I was just following the chapter, okay? But I tried to make it more understandable than your book. Here, let me show you. Here's how your book does it. Not as pretty. I would be pretty sure that you won't like that better. Okay, I tried to make it a little bit nicer for you as much as I can. It's very tricky and gross. Okay, but I tried my best to make it digestible. If you want to go through your book, let me rephrase. You should go through the proof in your book and read that as well, and that'll help cement your understanding. But I would recommend if you didn't get this the first time, go back and rewatch the video and see if you can get it the second time through, and then go through and check out your book, because I think your book is going to be um, more difficult to understand rather than less difficult to understand, because I tried to make it pretty and cute as much as possible. So that being said, if you totally don't get this and it makes no sense, it's not the end of the world. Okay. After equivalence relations, we're going next week, we're going to start into combinatorics, which is completely different, totally unrelated to all the things we've done so far. Okay. So if you don't get this, it's not the end of the world. We're moving on to something new next week. But put a bit of effort in and see if you can figure out what these things are actually saying, and especially the syntax of the symbols and how all the symbols are used and how they fit together. I mean, that's why we did like a million examples, right? So that when we use this big U, you know what the heck we're talking about. When we say reflexive, you know what the heck we're talking about, right? That's why we did a bunch of practice with all of these sort of vocabulary terms, this notation that we've been using. So hopefully what you should understand at this point is you should definitely understand each separate piece of notation and what it means. Now, putting it all together in a proof, that's another story, okay? But at minimum, you should understand each separate piece of notation and what it means. And you should take that knowledge and try to put it together to understand what the proofs are doing. If you are struggling with that, which I would assume many of you probably are, because this is very tricky, go back and watch the video again, and then check out the proofs in your book and see if you can work through it that way. Any questions before we take a little break here? Okay, sounds good. Well, let's take 10. We'll come back and do some practice problems. See you soon. All right, so we're going to do a couple of examples here. Seth, there is some problems with the 8.1 web work. I'm going to try to fix that up tonight. But if I don't get it fixed by tonight, then you should just skip it, and I won't count those questions. Yeah, there's something changed with the web work programming protocols. Yeah, okay, cool. All right. So what we're going to do is we're going to look at some relations, and we're going to first of all, decide if they are equivalence relations. And then second of all, talk about the equivalence classes of that relation, right? So here's one for you. We have a relation over the integers where x relates to y if and only if 3 divides x squared minus y squared. Okay. Okay, good, Tamara. Yeah, I'll talk to you after class. Okay, so I want to show that, first of all, that this is an equivalence relation. So how am I going to do that? Okay, symmetry, transitivity, reflexivity. So let's start with reflexivity. So we'll say Does 3 divide x squared minus x squared? Okay, well, that's the same as 3 divides what? 0, which of course it does. So we got that one. Okay, how about symmetry? Well, that's 3 divides x squared minus y squared implies what for symmetry? Good. 3 divides y squared minus x squared, which it does. And how do we know that? The difference will be a multiple of 3 either way. That's true, but can you say a little bit more? Like if we have, what's the relationship between x squared minus y squared and y squared minus x squared? Yeah, flips from positive to negative or vice versa. It flips sign, right? And so if 3 divides, let's say this thing is equal to -6, right? 3 divides -6, so of course then 3 would divide +6, or vice versa. If 3 divides 12, then of course 3 will divide -12. So it will be symmetric. So we got symmetry. How about transitivity? Right, so for transitivity, that one's a little bit more interesting. We have 3 divides x squared minus y squared, and 3 divides y squared minus z squared. We can translate those by definition into some equations, which is to say 3k equals x squared minus y squared, and 3l, or let's say m, equals y squared minus z squared, right? If we add those equations, we'll get 3k plus m equals x squared minus z squared. So in conclusion, 3 divides x squared minus z squared. Check for transitivity. Right? And now we've shown that R is in fact an equivalence relation. Any questions so far? Does that look okay? Okay, so let me ask you this. What are the equivalence classes of R? And let me start with a sort of a question about strategy. So how should we try to understand the equivalence classes of R? How should we try to figure out what they are? Any ideas? Okay, so yeah, so maybe each, so kind of both, right? So I think you guys both have a good idea there. So we'll take some squares of some numbers mod 3, and then take some squares of some other numbers mod 3, and see what their relationship is, right? So for example, let's start with 0, okay? And say, does 0, who does 0 relate to, okay? In other words, 0 is going to be in an equivalence class, right? And the question is, who else is in that class, right? So we'll start off with 0. Who else is in there? Any ideas? If I have 0 squared minus something squared has to be divisible by 3, what other something squareds can we get? Okay, any number x. Okay, so Sean, what are some examples of those kinds of x's that would work? 3, okay, anyone else? So all the multiples of 3. Okay, and 9 would also count. So 9 would be another multiple of 3. What if we did like 1 or 2 or 5 or 8, some non-multiple of 3? Could any of those be in the same equivalence class? David, you say no, and that's great. The reason why is when you square a non-multiple of 3, you're not going to put any factors of 3 into your product, because you have a non-multiple of 3 times a non-multiple of 3 gives you something that still doesn't have any factors of 3 in it. So the equivalence class of 0 will be 0, -3, 3, -6, 6, yada, 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 all the positive and negative multiples of 3. Okay, so what should I do next? What other equivalence classes should I think about?
So there should also be an equivalence class of all of the numbers whose squares modulus 3 are 1 and all of the numbers whose squares modulus 3 are 2.
Awesome. Okay, let's start with 1 and see how that goes, right? So of course 1 is going to be in here. Who else is going to be in here? 2, good. Because 2 squared is 4, and 4 modulus 3 equals 1 as well. So we've got 1 and 2. Well, that's interesting. Okay, of course 3 is not in there because these equivalence classes will be mutually disjoint, and 3 is already in the other one. 4 and 5 are also going to be in there, right? Because 4 squared is 16. 16 mod 3 equals 1. 5 times 5 is 25. 25 mod 3 equals 1. Right? Of course, we have all the negatives as well. -1, -2, -4, -5, dot, 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 dot. Which begs the question, what's in the equivalence class of 2? Well, there is no separate equivalence class of 2. There's only equivalence classes of 0 and 1, and that's it, because this covers all the rest of the numbers for the equivalence class of 1. Which is a little bit surprising, right? Because I forget, I think it was Sean, right, said that we could have an equivalence class for 0 and 1 and 2, but it turns out that the way that these squares work is everything that would have been in the equivalence class of 2 actually gets forced into the equivalence class of 1 because of the way that those squares are working. What do you guys think? 2 equivalence classes for 0 and 1? Questions? See how the idea of a partition, these mutually disjoint sets, is pretty helpful, right? Because you can see, oh, well, I can't have a 3 down here because a 3 is already up here, right? And that's not only an intuition, but it's a thing that we rigorously proved. So you know that it's true, right? Okay, let's do another example. All right. Let's say we have a relation R goes from R2 to R2. All right. And here's our relation where the point xy relates to the point wz if and only if x equals w. Okay, so hopefully you guys, are you guys comfortable with proving that this sort of thing is an equivalence relation? Do we need to do another one of those, or are you happy with that? Or should we just jump right into the equivalence classes? Okay, you feel okay with those. Perfect. So let's just talk about the equivalence classes then. What are those going to look like? And so we're going to have x equals w. So one equivalence class would be the equivalence class of the points 0. Let's use another variable, a. Sorry, the equivalence class of the point 0a, pardon me. Okay. That's anything that has an x coordinate of 0, right? Because those things are all related to each other. Here, the first coordinate, x and w, are equal, right? So for that equivalence class, the first item of that pair is going to be constant. It has to be for everything to be related to each other. They all have to be equal in the first coordinate, right? And so really what this is just saying, okay, everything that has an x coordinate of 0 and a y coordinate of whatever you want, those are all going to be equivalent to each other. Again, you're picking out one property of the point, which is the fact that the first coordinate is 0, right? Let's do, can someone think of another equivalence class? Yeah, 1a, right? The point 1 comma a is another equivalence class, and there are lots of these, right? In fact, an infinite number of them, because you could pick for your first coordinate any real number that you want, and there's an infinite amount of those, right? So altogether, these are all the equivalence classes of A and of R, pardon me. And if you think about what's happening here, what you're doing is you're taking an entire line. Let's do this example. So we have, this point 1 right here, right? And what we're doing is we're saying, well, we have this line that passes through the point 1, right? And what we're doing is we're taking everything on that line and saying that they're all equivalent to the point 1 comma a, right? So all of the x coordinates have to be, everything on this line is all equivalent to this representative, right? Which is the representative x equals 1 and y is whatever you want, right? We could also have another one, 2 comma a. Let me do my dot, dot, dots down here. So we have, another line right here, right? Where this whole set of points on this vertical line are equivalent and therefore being represented by this point in the equivalence class, right? What is this equivalence class doing? What is this relation doing? Would you say? Does anyone know the name of, if you take everything and squish it down to the x-axis? Does anyone know what that's called? Let me ask the question a bit different way. Yeah, projection. Yeah, that's exactly right. Pairwise squish. I like that. That's really good. But the technical term is a projection. Right? And really what I'm asking is, what if we only considered the representatives of the equivalence classes rather than the equivalence classes as a whole? We have this representative, this one, this one. What are we actually going to get out as the set of representatives? Well, that's going to be just the x-axis that's left, right? Which is a projection because everything gets squished down onto the x-axis. Okay, we're going to keep going with that same sort of idea. with a couple more examples, and then we'll jump into the lab. Oof, maybe 2 more examples is all we'll have time for. Okay, so let's do this one. So let's say R, again, goes from R2 to R2. Okay, and I want X relates to Y if and only if X and Y lie on the same line emanating from the origin. X and Y are collinear on the same, your book says half line. It's like a ray. No, I'll just call it the same ray. It's a better term for it. From the origin. Okay. So let's think about this for a minute, right? We've got our plane here. We've got a ray emanating from the origin like this, and we've got 2 points on there, X and Y. Okay, we have, let's call them X1 and Y1, which are related, right? X1 relates to Y1. We have a different ray coming out that way, where we have, X2 and Y2 are 2 different points on that ray. Okay, so what would our equivalence classes look like, do you think? Y equals C to the n of X. I'm not quite sure what you mean by that, David. Could you say more? Any point along a linear equation. Okay. I think that would be if you had not rays, but instead sort of entire lines. But this ray here doesn't extend out backward the other way, right? Let me ask a different question. If you wanted to only have a set of representatives for all of the different equivalence classes, what shape would that set of representatives make? Okay, so Lucas, you're on the right track. Yeah, a circle, a unit circle, right? Because if you have a unit circle like this, right, then any ray that you have coming out, right, and there's all kinds of points along this ray, they're all related to each other, which means they're all related to that particular point where that ray intersects the unit circle. So this could be the representative. That's the representative point there. And any given ray can be described with a single theta. Yeah, exactly. Yep, perfect. Yeah, that's exactly right. So that's so the theta, cosine, and sine, that's the trigonometric way of looking at it. Here's a geometric way of looking at it. Either way is fine, right? Okay, so I think you guys are getting it. Let's try one more. Okay, so this one's pretty fun. So so R is going to go from, oh, so Sean, you have a question. You may have to disclude it so it's not in all of them. Oh, 0, 0. Oh, thank you. Yeah, great question. Got it. Yeah, so yeah, we might have to eliminate 0, 0 because that would be in multiple equivalence classes, which is not allowed, right? This would be in all of the equivalence classes, which is not permitted, right? All of the equivalence classes have to be mutually disjoint. So I think the way that we could fix this, and I think your book, oh yeah, your book did say that. I just missed it. Nope, so good point. I screwed that one up. this relation is actually, we have to change the domain and codomain. So this will be from R2 without 0, 0, the point 0, 0, to that same set, the real plane without the point 0, 0. That's better. Yeah, great. Excellent point, guys. Good. Okay. So this next one is going to be a little different. This is going to go from the set of all lines in R2 to the set of all lines in R2. Now these aren't lines through the origin, these are any old lines. So, so here's R2, right? So so this is a line and that's a line, infinitely long lines. They're all infinite lines, right? Here's another line right here, Okay, and here's our relation. L1 is related to L2 if and only if L1 is parallel to L2. So if this is, here's L1, here's L2, let's pretend that I drew this better and these are parallel. There, just make the lines thicker. That makes them parallel, right? And here's L3. So L1 and L2 would be related, but L3 would not, right? So again, if you squished all of these parallel lines together, right? Here's another one out here, another one over here, another one over here. We had all these parallel lines that are all related to each other, and you squish them together. My pinky and my pointer finger don't quite make it, but you get the idea. What is my set of representatives going eventually to look like? Line that's mutually perpendicular. Well, we don't need perpendicular. All we need is non-parallel. So if these are our lines, then this one, which is just like a little bit different, that one would not be included. So it doesn't have to be perpendicular. It just has to be non-parallel, right? Does that make sense? So if we call this L4, we would say L1 relates to L2, but L2 does not relate. That does not relate, by the way. It's an R with a slash, right? Does not relate to L4. Intersects them, sure. Any non-parallel line would eventually intersect them. That's true. But if we, let me ask my question from before, right? If we wanted to talk about the representatives of these equivalence classes of parallel lines, what would they be? Not a box, not quite. So the set of all representatives of equivalence classes of parallel lines would be what? The same as when we had which were vertical lines, which were also parallel lines. Not exactly. It's kind of a projection, but you have any line like this, right? These are all parallel to each other, right? Anywhere in the plane, as long as my slope doesn't change like this, right? Any line on the plane that's still parallel is all going to be in the same equivalence class, which will have one representative, right? And then all the lines like this, those will all have the same representative no matter where they are. And there will be an infinite number of representatives. What exactly do you mean by that, David? Ray is going both ways. Not exactly. Close. So let me help. So the set of all representatives would be all the lines that go through the origin. right? Because if these are all in the same equivalence class, they're all the same when they have this, this same slope that I've got right here, right? These are all the same. Then we could say the representative is the one that happens to strike the origin. Oops, I screwed that up. There we go. The one that strikes the origin, that would be the representative. Right? And then if we, thought about all these lines like this, right? All these guys, well, we could think of this one as the representative for that. Right? And so could you represent those lines with a box about the origin? I don't think so. I don't think that's quite right, because you could represent them with all the different slopes. I think that would make sense, right? So you could say the set of all lines from 0 to 180, sure. You could say the set of all lines that pass through the origin with a particular slope, right? Yeah, half circle, sure. Yeah, I think that makes sense. Yeah, good. Yeah, half circle is a way of looking at it, but the issue is that we don't have points that are equivalent to each other anymore, like we did here. These points are all the objects of our relation, right? The inputs and outputs of our relation are all points, and that formed a circle. But here, the inputs and outputs of our relation are all lines, so it is a little bit different, right? It's all the lines that pass through the origin, who intersect a half circle at the same spot, right? Something like that. So why don't I leave it there? I'll leave it for you to do a couple more examples there. Oh, there's one more that's good, but we really got to get moving. Okay, so we do have to do the lab. Well, let me just describe. I won't ask you about it, but I'll just describe one more for you. How about that? We'll go quick. So here's the last one that I want to talk about. All right. So A is a set of points in a rectangle with X and Y coordinates between 0 and 1. That is, it's all the points in R2 such that, well, it's actually a square, right? X is between 0 and 1, and Y is between 0 and 1. And here's our relation, right? For all X1, Y1 and X2, Y2, the 2 points are related if they're equal to each other, okay? Or if X1 is 0, X2 is 1, and the Y's are the same, or the other way, X1 is 1, X2 is 0, and the Y's are the same, or Y1 is 0, Y2 is 1, and the X's are the same, or Y1 is 1, Y2 is 0, the reverse, and the X's are the same. In other words, all points along the top edge of the rectangle are related to the points along the bottom edge, and all points directly opposite from the left and right edges are also related. The points of the interior of the rectangle are not related to anything but themselves. Then R is an equivalence relation. Imagine gluing together all the points that are in the same equivalence class and describe the resulting picture. What do you think? You take a square, the left edge and the right edge of the square are equivalent, so you could say they're the same thing, which essentially means they're glued together. They are equal, right? Or they're equivalent. And you do the same thing with the top edge and the bottom edge. So what kind of a shape would you get in that case? Anyone see it? So here's my equivalence relation. I have this rectangle, okay? And I take the left edge and right edge and I glue them together, okay? Because those points on the left and right edges are equivalent. Then I take that rectangle, and here's the top edge and the bottom edge. It used to be like this. So here's the top edge, and the bottom edge, and then I glue those together. Didn't go very well, but I think you get the idea. A torus. Yeah, great, Lucas. You get a donut, right? If you take a square, right? Think about a video game, okay, like Asteroids, where you're flying in your spaceship, you fly off the top and you pop out the bottom right on the other side, right? Or you're flying in your spaceship, you pop out the right edge and you start on the left edge and just keep going where you left off, right? That is actually a donut, and you can think about gluing together different parts of the plane in terms of equivalence relations, and then think about the shapes that come out the same way that we thought about the representatives here, right? So that's another kind of nice example. Now I've ruined that paper. All right, so now let's talk about the lab. All right, let me stop this guy, share this thing, pop over here. And I have to remember Tamara at the end, so I won't forget you. And quickly leave like I always do. All right. So here's our lab for today. I got to remove that. Add this. All right, so for lab this week, you're going to be thinking about relations. And relations are really nice for 3D graphics, because if you only had a function in 3D, you can't have a surface that loops underneath itself, because then it wouldn't pass the vertical line test. And you saw that with your surfaces last week, right? You had a surface, but you couldn't have the surface. Let me do this real quick. You couldn't have a surface that looked like this, where you have it and then it loops back down underneath itself. Because if you did a vertical line test, you would hit the surface here and here underneath, right? But with a relation, you have no such restriction, right? So you could make this sort of wrinkly, thing that's still a function last week, but now this week with a relation, since there are no rules, you can loop it sort of all over each other. You can do like one of these and one of these, make like a little S shape, something like that, right? You could take it and loop it around both sides and make like a sphere. That's not a very good sphere, but I think you get the idea, right? There are a lot less restrictions, so you can make a lot more shapes, right? Sorry, and that paper crinkling probably sounded horrible on the audio. Sorry about that. All right, so let's trot through it, right? So we're going to have a similar setup to last week. We still have this vector, which is just going to be 3 doubles. It's like a point in 3D space. We'll have the same constants as before. We'll have a resolution of our cubic grid, okay? This time our grid is going to be 3-dimensional instead of 2-dimensional. The rest is all the same. And here are my function prototypes. A lot of them, okay? Still got normal, draw triangle. Now I also have draw cube, which is going to be useful. R is going to be my relation, okay? And another function called intersects, okay? So let's go check them out. Lighting's the same, normal's the same. Draw triangle, you can see that's the same, right? And begin triangles. Then I call my normal function for the lighting, then set that up so that the reflections work correctly, and give it the 3 vertices to make a triangle, right? What's a cube? Well, a cube, first I make 8 vertices of the cube, because what I'm doing for my arguments to the function, I send it a position. That's going to be the center of the cube, right? It's going to draw a vertically oriented lit cube centered on pos. Okay, now pos is a vector, so it's a point in 3-dimensional space. And then side is the length of the cube, right? Length per side, and I'm going to draw it using 2 triangles per face, right? So first I build the 8 vertices of the cube, right? The 8 corners of the cube, right? 4 on the top of the cube, 4 on the bottom, right? 8 corners on a cube. Here they are. And I calculate those by taking the position from the center and subtracting half the side length. or adding it, depending on which way I'm trying to go. Once I have the 8 corners of the cube, I can draw 2 triangles per cube face. So, man, maybe I should draw this. Are people following this? Does this make sense? See what I'm saying here? Okay, we got a yes. Anyone else? Anyone lost? I have no idea what I'm saying. I'll just go real quick here. I think you get it. Okay. So here's what I'm saying. We've got a cube. Okay. The center of the cube, the very middle, that's going to be pos. And the length of this guy, they'll all be equal. This is called side. That's just how big the cube is, right? And what I'm saying is I have the corners. There are 8 of them. Here's the corners. 1, 2, 3, 4, 5, 6, 7, 8, right? And for example, on the left face, the way that I'm going to draw this square for the left face of the cube is by drawing 2 triangles like this, right? And the vertices of each triangle are going to just be the corners of the cube, right? So here's triangle number 1 is these 3 points. Triangle number 2 is these 3 points. So each square turns out to be a dozen triangles, right? 6 faces times 2 triangles per face. Does that make sense now, Seth? Picture's worth 1,000 words, right? Anyone else still lost? Makes sense. Okay, excellent. So that's how I'm drawing cubes, okay? Now, it gets a bit more complicated than that, okay? So I'm drawing cubes. Why am I drawing cubes? Well, here's what I'm going to do. Here's my draw object here. I set up my size of each cube to be 2 divided by my resolution, because remember, the window that I'm drawing in is going to be -1 to 1 in all dimensions, which is the total area, the total volume that I can draw in is 2 by 2 by 2. I divide that by my resolution to get the individual little cubes inside. So think of a Rubik's Cube, right? That's a 3 by 3 cube. So that would be a resolution of 3, right? Where, you know, you would divide that bigger cube into 27 smaller cubes, okay? But my resolution's 100, so it's going to be a lot more little baby cubes, right? And what I'm going to do is look at each cube in the grid, okay? So if my resolution's 100, the total number of cubes will be 100 cubed, which is 1,000,000, okay? Got 1,000,000 cubes. I go through each cube, and if the relation intersects my cube, remember the relation is this surface that can curve under itself. It can sort of spin all around and twist all around in space, okay? So if that surface intersects this little tiny cube, then I'll draw the cube, right? Calculate the position of the cube and draw it if that cube is intersected by my relation, okay? So think about this for a second. You have this big old grid of cubes, okay, a 3-dimensional grid of cubes. You have a surface that curves and twists inside of that grid of cubes. And what you want to do is only draw the cubes that the surface intersects, right? Thanks, David. I appreciate that. Yeah, I thought it was a clever idea. It's kind of a nasty hack, but I'm all about those. that's how I roll, right? Nasty hacks. So so if you draw only the cubes that the surface intersects, then you'll get a crappy looking, sort of cube looking version of that surface. Okay. Let's run it. Let's see, what do I have going on here? Nasty hack. Yep, absolutely. Here, let me turn this off. Okay, so there's the intersects function and the relation. Okay, so let's turn on a pretty straightforward relation. All right, got x² + y² + z² is less than or equal to 0.9. which should make a sphere. Now, I haven't gotten to the sort of heart of the matter yet. There's one more thing to do. Right? So before I get to my intersects function, which is actually the clever part, let me show you what it does. Oh boy, is this gonna do anything? Oh, let me go the other way. Let me turn down my resolution. That resolution's way too high and my laptop is not fast enough. So let's make this look way crappier. Let's do resolution of 20. Remember, this resolution is cubed. So if I do 20 cubed, that's going to be much, much better than 100 cubed. Right? Big O of n cubed is a whole situation. Okay, so here's my crappy one. There we go. Now it works just fine. Right? And you can see it's a sphere made of cubes. Right? I can actually even go inside of it. And now I'm looking at the interior of that sphere of cubes. Is this calculating the function every time? Oh boy, I hope not, but probably. It should be hollow. Yeah, Seth, that's an excellent question. And Lucas, I know you're the graphics guy, right? I'm almost certain that I did this in a horrible way. And if you have any suggestions for me on how to fix it, I would love to hear them. Graphics is not my forte. It's just fun. So yeah, any suggestions would be very much welcome, or from anyone else that knows about graphics. So yeah, is it drawing it every time? I don't think it is. I don't know. That's a question for another time. So I got to finish this up here. That's a great question, Lucas. I'll think about it. Yeah, it is hollow, and it's supposed to be hollow. Okay, here's why. Even though my relation was less than or equal to, I need to show you how the intersect function works. Okay, so here's the intersect function. It says we do the intersection for this particular cube, right? And this is just computing where the location of the cube is in space. So it's like, where is that cube? And here's how the intersects function works. It's, again, #NastyHack, okay? What I do is I make up a count of how many vertices are in the surface. And then I check to see if some vertices are in and others are not, okay? So here's what's happening. Let me go back to my picture of a cube for a moment. So let's say that this cube happens to lie on the surface of the sphere, like this, right? Then these 4 points would be in the relation. These are all in the relation, and these are outside the relation, right? Maybe, you know, this is that's my shading on my sphere, okay? So the curve of the sphere cuts right through this little cube, right? Now what I'm doing is I'm counting up how many of the 8 corners are inside the relation and how many are not. And if it's the case that some of them are inside and some of them are not, then I know that this particular cube lies on the surface of my relation, right? If all the corners are inside the relation, then I don't draw that cube, right? Because I know that the surface is not cutting through it. Or if all the corners are out here, well, similarly, then I know that the surface is not cutting through that cube, right? So I only draw the cubes that have the surface cutting through the middle of them somehow, right? Now it could be that it's 4 and 4, or you know, maybe my cube looks like is on the surface here, right? And I have only 1 corner inside the surface and 7 outside. That's fine. I would still draw it. Let me show you the code. So what I'm doing is I have this Boolean function, right? Intersects. Does the cube intersect the relation or not? And if the count is greater than 0 and less than 8, what that means is some vertices are in the surface and others are not, or some vertices are in the relation and others are not. And those are the cubes that I want to draw. If it's all the way inside, I won't draw it. If it's all the way outside, I won't draw it. It's only the ones that cut through the middle of it, right? And to do that, I run my relation on all 8 corners and count up how many are true and false, right? Again, my relation is also a Boolean function, right? So that's why less than or equal to makes a shell instead of a solid sphere, right? Does that make sense? Because some of the points on the cube are going to be a greater distance than 0.9 from the origin, and some will be less than a distance of 0.9 from the origin, right? Does that answer your question about it being hollow? Does that make people happy? Okay, so let's try another few of these. Okay, a diagonal plane. Here goes. X plus y plus z is greater than 0. Okay, so there's a diagonal plane, right? So you can see all the squares there, right? Those are the ones where some of the points on that little square lie on one side. They're more than 0, and others are less than 0. So sometimes it's true, sometimes it's false. And when you count up the number of true and false corners, you get a number in between 0 and 8, right? Let's try another couple here. Northern hemisphere. What I did here. So this is where it starts to get interesting. So I've got that these guys are less than 0.9 and y is greater than 0. So I'm using some logical connectives here to build, to combine different relations together. So now I've got part of a sphere and part of a vertical plane down on the bottom, right? Again, still hollow. I can zoom in. And here's what the, oh boy. There we go. Oop. There we go. There's what the inside looks like. There's the sphere part. There's the square base, right? All right. So here's the union of two planes. So I want to take two planes and draw both of them, right? Because what your assignment is, and we're out of time, so I should probably tell you what you're supposed to do here. Your assignment is to take a bunch of different surfaces and put them together to make a sculpture, right? The whole purpose this term is to make sculptures, right? So here's two planes, and the way that I got that is by ORing together these two logical expressions that have one plane at y equals 0 and another plane at y is at negative 0.5. But this one doesn't do what you think. Now see that these inequalities are both facing the same direction, whereas these ones were facing opposite directions. And this one doesn't make those two planes as you would expect. It only makes one of them, right? So why isn't it working, and how can you make a successful union? That's something to think about, right? That's part of your lab, is try to figure out how you can put these logical expressions together to make, you know, one sphere over here and another sphere over there, or you can make, you know, a bunch of blobs that fit together and make some kind of cool sculpture. See if you can figure out, instead of how making an intersection like this one, right, which you would use and, now you're trying to make a union, but or doesn't work all the time. It only works sometimes. The question is why, and can you fix it, right? And here's some fun stuff using only and or without figuring out the union part of it. So there's a pipe fitting, right? And of course, if you want to, you can make these, you can turn up the resolution a bit. Let's try for 50 instead of 20 and see if that still renders. It's going to be slow, but let's see how slow. You can mess around with R, and to do the union, you also have to mess around a bit with intersects. Yeah, so you can see with resolution 50, it's going pretty slow. It looks a bit better, but now my animation is going pretty slowly. It's probably recomputing, Lucas. That's probably what's going on there. All right, so that's the lab. Make yourself a sculpture, see what you can do. Mess around with those logical expressions. Intersection is pretty straightforward. It's already done for you, but union is a little tricky, and I'll leave that for you guys to figure out. That's all I've got for you. And Tamara, I will hang out for a minute, but before that, does anyone have any questions before we go? All right, sounds good. Well, have a good day, everybody, and I will see you on Monday. Yeah, sure, Seth, you can hang out too. No problem.